this kind introduction, and thank you everyone for joining this webinar and your interest in our work. So in the next 20 minutes, I will present the first part of this presentation. So basically today's webinar will be divided in two sections. The first one that will tackle the technical risks inherent with technical assumptions in financial models, and the next 20 minutes will be covered by my colleague Mike on the financial risk in PV investments and how to mitigate this. So with this being said, I will start with the first part of this presentation on the technical risks. And as a brief introduction, so I will give the background of how this study started within this task group. We will cover all the technical assumptions using PV financial models in the review we did, and we identify the weaknesses and we deliver recommendations for different project phases, going from PV plant design all the way up to operation and maintenance. We will then review a study we did comparing long-term yield assessments at the plant design phase compared against actual PV production of a portfolio of PV plants to review how these correlate. We will then cover the topic of risk quantification and economic impact and show the tools that are available today for this, and simply quick on the conclusions of this section before giving the word to colleague Mike. So as an introduction, we develop a survey of current practices. So basically we develop a questionnaire and we share it within the task group members and contributors. We collected input from 84 different PV projects spread across 9 countries, covering different business concepts. We complemented the information collected from this survey with results from the solar bankability project. For those that are familiar with this project, this is a European Union Horizon 2020 funded project, and you can find all the results in the website, which I will share with you also the links. And we complemented also the results with general and public domain industry. So I will directly start with these figures that shows the energy flow from sunlight to consumer of electric power, with the aim of showing that there are several submodels and assumptions that are linked with several uncertainties. So going from this sunlight all the way to electric power involves many models, and these models are used to calculate the initial long-term yield assessment of the plant, and each of these sub-steps has a related uncertainty with it. So what we did is to evaluate this and try to identify the main weaknesses to propose some mitigation measures and recommendations on this regard. So as I said before, we covered different project phases all the way from the beginning, from the early plant design phase up to the operation and maintenance phase. During these next 20 minutes, of course, I will not have time to cover the entire process with all the weaknesses and recommendations we do. So I've selected for the presentation today the most important points and aspects that we should focus and we want to discuss with you. And then I invite you, of course, to read our full report where you will find the details for all the other elements. I will share with you also during the presentation the links where you can download our report and continue the reading. So starting with the PV plant design, the main weaknesses we found is starting with the solar resource assessment. So we saw that the effect of long-term trends in the solar resource is often not fully accounted for. Even though there may not be long-term trends all over the world, several studies have shown that there are some trends, especially in Europe or in Asia. And we saw that current practices today often do not take into account this effect, which means that by taking the last average of the last 20 years or 30 years, we may introduce in our models the effect of this lower irradiation or higher irradiation in past years. What we did together also with the Solar Bankability Consortium is to develop some models as recommendations on how to account for not only in the P90 values, but also tackling the uncertainty steps. Continue with the uncertainty topic. We also saw that one of the main weaknesses today in PV plant design phase is that exceedance probabilities. So we calculate, for example, so-called P90 or P75 or all values are often calculated assuming that all the uncertainties related with the modeling are normally distributed. While this can be true for some of the uncertainties, like for example in the figure you see now, it's exactly the same data as before, so meaning average irradiation out of 32 meteo stations in the Netherlands. In this case, it shows that can be indeed approximated to a normal distribution. Red for a normal distribution. You see in the blue dots the empirical data, but you see already that there might be some differences. In this case, we had more than 55 years, I believe 58 years of data, which is always the case. So what we want to stress here, and what I invite you to read the report for further details, is that there are several uncertainties that might be considered, but there are certainly others that are. This will be also covered in the second presentation. Continue in the PV plan design phase, we also saw two main weaknesses, one related with the degradation rate assumption, especially the rendering of the system behavior over time. That this is today starting to be a topic that is discussed more and more, but still there are some weaknesses how this is taken, especially on the. Another important point that we want to stress out is the availability assumptions that we saw during the survey that we performed, that often availability assumptions initial phase of the design project design phase are not always the same as the availability assumptions, availability warranties during. I will come back to this point later with an example slides from here. So therefore our recommendations for the plan design phase lie mainly as a summary on even tackling as a very early stage on project pre-feasibility, rerun the financial models as the plan takes physical shape on the design. Possible or almost impossible to ensure that whatever it was decided at a very early stage. And so our recommendation is to rerun all the financial. Often elements can change, design concepts may change as well, so this should be constantly. Also we stress out that the quality control is critical for enabling the realization of the final. Do all the best assumptions at the design phase. We need quality control to ensure that everything that was taken into account in this early stage actually true. We stress here the 10 times rule, which is basically it says that finding and correcting errors at early stages are expensive compared with later stages, and we touched this point a couple of times during today's class, which basically says that, for example, fixing and correcting an error in a design phase can 10 times cheaper than the phase or 100 times cheaper operational phase one. Also very important to ensure back-to-back warranties between EPC and O&M to ensure that also the financial, the realization of the financial, or minimize events that are not covered by the warranties or warranties. During the plant construction, we also saw to our survey that there is often an absence of a standardized transportation and handling protocol. In some cases it does exist, but it's not detailed enough. And what we observe also inadequate quality procedures, especially for the component unpacking and handling during construction. Again, coming back to the 10 times rule, this is a very sensitive, even if quality control is applied in factory inspections, for example, can be generated during the transportation packing, and this manifests costing much. So overall, we see that there's a lack of construction supervision. By implementing some supervision, we could.
Sorry, Mauricio. If you can maybe speak a bit louder, it would be great. Thank you.
Yes, thank you, Fernando. During the plant acceptance, we also observed some weaknesses, like inadequate protocol for data collection. So often data is now a topic that is more and more common, but the protocol for the collection of data and the calculation of key performance indicators like performance ratio or availability, or even going to visual inspection, is often not fully or correctly defined. We also observed a lack of relevant equipment for example, infrared imaging or electroluminescence devices. And in some cases, we even also observe a lack of short-term performance tests at provisional acceptance. As recommendations for these two phases, so mainly the procurement and construction and the acceptance phase, a recommendation is to ensure the quality control for the hardware, but not only the hardware, so also the workmanship and the software. So that means that hardware can be controlled and can have a very good quality, but if the workmanship does not perform as it should, it could introduce some other issues in the hardware, and same for the software. So quality should be in all phases of the project. It's what I said also before, to apply the quality before leaving manufacturing, but also upon a site arrival and also even at plant acceptance. We also tend to recommend that EPC warranties should ideally cover at least 2 years to enable the discovery of some deficiencies during the first year and the effect of the correction measures during the second year, and even sometimes it's recommended to have a 3-year period to go for a smooth transition into the operational phase. And here we come again to the 10 times rule, because deficiencies found during acceptance, for example, may cost 10 times more than during construction because it's a later stage and we need to correct some errors. But at the same time, this will cost 1/10 of what it will be during the operational phase. So that's why it's very important to apply mitigation measures as early as possible. Now moving to the operational phase, we saw that the selected monitoring system is often not capable of advanced fault detection and identification, while in the past it was not very common to have a monitoring system. Today it is becoming state of the art, so almost every PV project now includes a monitoring system, but not all of them are capable of advanced fault detection. And with today larger plants and being constructed in different environments, is becoming more and more important to have a monitoring system that can detect some deviations on time, especially for larger plants or remote areas as well. We also observe missing, in many cases, or inadequate maintenance of the monitoring system. So also the monitoring system that is a software needs a maintenance. It is also related with several hardware devices, and as any other pieces on the project, it needs to be included in the O&M scope of work. We also saw some deficiencies in some cases, but not in many, about the preventive and corrective maintenance protocols. And again, during the operational phase, we also see inadequate or even sometimes absent relevant equipment like infrareds or electroluminescence devices. Therefore, our recommendations for the operational phase is basically to ensure to have an advanced monitoring system, but most important is to have O&M operators that can react on the monitoring system signal. So it's like in any case, it would be one can have the best tool at hand, but if it does not have the people to use the tool, then it's not exploited as its maximum. It's true, and is what I was saying before, that without accurate advanced monitoring today is harder and harder, or there is almost little possibility for optimizing operational activities, especially in large plants. And then what I said before, so the first years of operations are critical for meeting the financial model, and here that's why we talk about the 2 up to 3 years, including the first year for detecting some faults and repairing them as soon as possible, still within warranties periods. The second year for verifying that the faults have been rectified, because actually in PV also many faults do not appear and are not always catastrophic, so they won't be easily found at the beginning. So that's why it's very important to do and to still look during the second year if everything has been solved. And the third year is more like for contractual obligation, as I said, to enable a smooth transition from the warranty period into what we said, the bottom of the bathtub curve during the operational life of the PV. Now I will go into the second parts of basically what I said at the beginning in the outline. I will show you the summary of an exercise we did where we compare the initial estimates, long-term yield estimates of a portfolio of PV plants, and we compare them against the actual production of these 41 PV plants. Basically in the figures you see the difference between the expected, so the estimated long-term yield, and the actual production of the first year of the plants, meaning that the 0 line would mean that the estimates were exactly the same. Of course, this is not always the case. And then you see in red and green the P90 and P10 confidence interval. So basically what was estimated at the long-term yield assessment phase. You see that for most of the plants, the actual difference lies within these margins. However, we observed also some what we thought outliers, but the differences were too high. So we investigated a bit more in detail, and we found out that for many of these plants, for the majority of the plants, actually the availability was an issue. So meaning that the initial unavailability that was assumed or was considered in the initial long-term yield assessment was not the same as the actual unavailability these plants were having during the first years of operation. So we corrected to have a fair comparison. In this case, we wanted to see how good today state-of-the-art methods for long-term yield assessments are. So we corrected for this unavailability, and you see already that these outliers disappear. And most of the plants within the portfolio now lay within the expected uncertainty ranges. We observe a small, around 1% overestimation, or could be also underperformance. Not the purpose of this to discuss this further, but you can find more about this topic on the report. But basically, what we should learn from this exercise is that for most of the PV plants across the portfolio, the actual electricity production during the first year of operation, as I said, lies within the expected uncertainty ranges. So it means our uncertainty ranges are realistic. In some cases, you saw in the figure before, this is larger, but overall the portfolio, they are in the same range of magnitude. And the actual availability, and this is something very important, and that's why we also stress it as a weakness before in one of my previous slides, is that the actual availability is lower than initial estimates in long-term yield. That's why we should ensure back-to-back warranties as well, and what was assumed in the initial long estimates actually is true during the operational phase. At portfolio level, we see that the yield is slightly lower than the initial estimated, but as I said, it was in the order of magnitude of 1.1%, so it's not relevant. It's not very big, the difference. The reasons maybe, yeah, we can start from this. But what is interesting and to stress is that actually the dispersion, the root mean square error across the portfolio is around 4.4%, so which shows that actually these deviations are typically expected mainly because of the variability of the solar resource. We should not forget that, of course, the initial long-term yield estimate at the beginning of a PV plant was done using average solar resource of the last 20 or 30 years. So that means, of course, that the first year doesn't necessarily will be exactly the same. So there is within this 4.4 margin in this case, and also other site-specific losses that are not precisely modeled during the design. But overall, the conclusion of this analysis was that today long-term yield assessment methods are very good, and we can trust also on the estimate. But this exercise helped us to see some weaknesses we could still correct. And now the question also, and here I'm using a slide that was presented in a previous session from a colleague of me, Magnus, during the Intersolar this year. Actually, we present the results of the solar bankability project that I mentioned also before, where we developed a systematical approach to quantify the risk. Okay, so if have a tool that helped us to quantify the risk and also to be able to answer the question that what is the benefits of mitigating the risks. So basically the cost is driven by CAPEX and OPEX, and if we continue to decrease this, we can of course decrease the LCOE as well, but then this might incur in higher risks. On the other hand, of course, if we apply mitigation measures, we will increase the CAPEX or the OPEX or both, depending on which kind of mitigation measure based on the project we are implementing them. But of course, the question that we want to know is what is my benefit? So basically, what we did is to develop the cost-based FMEA, what we called on the solar bankability project the cost priority numbers. I will show you in the next slide what is basically this, and you can find it but more detailed with the entire report on the solar bankability website that I have the link here in the screen, so it's www.solarbankability.org, where you will find all the explanation of this methodology. But this basically complemented what we did on the IEA PVPS Task 13 group, where we analyze the long-term yield estimate and their level of confidence. And on the other hand, we see also a feasibility study based on project-specific assumptions that you will see in the next presentation, Mike. So basically, this cost priority number methodology that was developed within the solar bankability project was the first approach to implement a cost-based FMEA to the PV sector. The methodology is based on a statistical analysis, but also some assumptions, and it's basically looking at the cost of loss for system downtime, for example, but including this information and combining it with cost for detection of faults or issues and mitigation measures. And also we take into account further factors like, for instance, the occurrence of faults, irradiance levels, power loss, power purchase agreements, and others. So I invite you again, of course, I will not have the time to go through the methodology in detail here, but you could go to the Solar Bankability website where you'll find a full description report of this tool. That is basically a tool that is or can be used to benchmark different mitigation measures and to actually answer that question of if there is a benefit on applying in it. So I invite you to go there and read and play a bit with this. So the conclusion of this first part of my presentation is basically that the main areas of weakness in a PV project are from inaccurate assumptions for future behavior, but basically the lack of methods to enable these assumptions during the design, building, commissioning, and O&M. And overall, we see a lack of quality control through plant's lifetime. Quality is applied often in different phases, but not in all. And we saw that applying quality control throughout the project, it could help to reduce drastically several issues. And then we saw also just now that the benefit of individual mitigation measures can be calculated today using the cost priority number methodology that was developed within the solar bankability project. And finally, the keys to ensure that a financial model holds true is to have, of course, in one hand, accurate assumptions for the future behavior, which seems today, using state-of-the-art methods, we can be very close. But as I said before, key is to ensure that the assumptions are enabled during the design, during the construction, commissioning, but also, of course, during the operational phase. And as I stressed before, we need high level of quality control throughout the plant lifetime. And with respect to the technical risks, the focus on the technical aspects of the EPC and O&M scopes of work to manage the technical risks linked to the CapEx and OpEx of PV investments in the best way. And I invite you to read the report. So you can find the full report on the IEA PVPS website. You have the direct link here with an ID number, or of course you can simply go to iea-pvps.org and then browse into the task 13 and you will find our report there with more details of what I have just presented and also covering the next presentation that might give in some minutes. And finally, also for those that will be in PVSec in Amsterdam this year, I invite you to also join us in a workshop for the PV system performance and PV module reliability, where we will present further this same work, but also all the other work from the colleagues from the Task 13 group. This will be on Tuesday, 26th of September, on the morning parallel session during the evening. And with this, I've concluded my section, and I will give the floor to Mike Green. Thank you very much.
Hello, everyone. Thank you all for joining us today, and I thank Maurizio for a discussion on the technical assumptions and their weaknesses, the level of confidence we can have to date for the accuracy of these assumptions, and for touching upon the newly implemented failure modes and effects analysis that we suggest being used in our field of PV development for mitigating the technical risk, and the use of the cost priority number, or CPN, in quantifying the cost of risk. I direct you all to our recently published report, as Maurizio did, the technical assumptions used in PV financial models, for an in-depth description of these methods. And now we will spend a few minutes discussing how we can attempt to mitigate some of these financial risks. There are two distinct phases in a PV project: a feasibility design process defining quality and costs, leading to a decision to proceed, then licensing and financing. Once a project is licensed and financed, we consider it shovel-ready, and we begin the process of finding a contractor and building the project. It is important to recognize that there usually does exist a timeout between the two phases. During this time, projects often undergo changes in personnel, sometimes even ownership. When the project comes out of this timeout, it is important to ensure that the initial design and design parameters chosen during the first phase are adhered to or properly recalculated for the second phase. PV projects, particularly large ones, are financial endeavors first and foremost. As such, the mover of the project is often more of a businessman than an engineer. At some point, a technical simulation is performed to figure out how much energy can in fact be produced on the piece of land or rooftop under discussion. To this end, some form of simulation program is used, such as PVSYST or PVSOL or SAM, or proprietary in-house spreadsheet. A selection of such simulation methods are discussed in our recently published report, PV Performance Modeling Methods and Practices, that can be downloaded from the same IEA PVPS Task 13 website from where you can download this report. It is important for the PV developer to understand that these modeling methods must be operated by an experienced user fully versed in operating this program. One of the interesting results that came out during one of these modeling workshops was that even users of the same software package modeling the same project can come up with very different end results. 4 users came up with results spanning values with a 15% spread. This is due primarily to the choices made by the operator when choosing the simulation characteristics to be used by the program. We therefore suggest that the development characteristics to be used by the development team runs simulations using different operators, and that the operators then discuss between themselves the choices made that are responsible for any difference in results, and then to analyze the actual level of variance that should be used with the solar resource parameter in calculating the financial output for the project. What all these methods have in common is that they use many parameters, starting with the solar insolation and land and roof size, then subtracting losses due to any number of reasons from soiling to shading. Here we see on the right the loss tree that represents the losses calculated by the simulation program. Starting from the solar resource, the simulation process calculates the effect of all mitigating parameters on the solar resource based upon the module construction parameters, inverter construction parameters, module inclination parameters such as tilt, azimuth, and self-shading, soiling, back panel temperature, and many others, until a final energy to grid value is output at the bottom of the tree. To calculate these losses and to arrive at the primary conclusions we are looking for, namely energy generation, revenue, and the internal rate of return, also known as the IRR, we use a number of parameters. We can differentiate between 2 different types of production parameters, system and loss parameters. Here I have listed only some of the parameters of each of these 2 production types. System parameters would include the module power, solar resource, the ground or roof coverage, the module tilt, and the array azimuth, to name a few. Loss parameters would then include the shading, soiling, temperature, initial degradation, and the animal degradation, among others. And then we have our project parameters, primarily derived from the regulatory and statutory environment of our project, as opposed to the physical and technical elements. These parameters include, among others, our licensing costs, installation costs, unavailability, operation and maintenance, fixed cost, and the contingencies. All these parameters are used in calculating our 2 primary equations, our total energy and then our profit. First, we calculate our total energy, accomplished for the most part by an experienced operator of a simulation program who will supply us with the total energy for the first year of the project, which is the solar energy minus the sum of our losses. This value for total energy is then used to calculate the profit, which is a function of the total energy we just calculated and the time and costs, including the taxes, insurances, etc. In our newly published report, Technical Assumptions Used in PV Financial Models, I do believe that we have explained well how to achieve high-quality parameters. However, the best quality parameter is still accompanied by a variance that can be as high, even more than plus minus 5%. This variance is a source of risk. 5% on the global radiation in a 10 megawatt plant is not insignificant. We have here 12 parameter values used in an energy simulation and for calculating the ensuing financial revenue. On the left, we have our well-known parameters that we use daily in our discussions and calculations. The module power is, of course, the watt peak of the panel. Then we have our site parameters, which include the horizontal global irradiation, irradiation decrease or increase due to the tilt angle, and the ground coverage ratio. Following that, we have our energy yield assessment parameters, including our irradiation loss due to shading, losses due to soiling, module loss due to temperature, and the module loss due to LID or the light-induced degradation. After that, we have our capital expenditures, our turnkey installation cost, our power production and power sales, which are dependent upon, among other things, the technical unavailability, and the PV system or PV module degradation after the first year. and of course our operational expenses, which we term as the fixed yearly fee. We are all quite familiar with these parameters. However, what are the variants of these calculations? What can we do to take the variance into account when performing our yield calculations and profit calculations? If we can run our yield calculations and profit analysis with not only accurate parameters, but also with each parameter's variance, we will have mitigated or qualified some of the risk. To this end, we suggest using the Monte Carlo method for simulating risk when calculating our yield and profit. This Monte Carlo simulation calculates our equations 10,000 times, using not just the parameter, but the variance as well. When programming the simulation, we must, however, define the variance and the type of distribution. Here we must exercise our understanding of the parameters in order to maximize the effect of this method. We see here that we have categorized on the right our parameters as per a type of distribution. In this case, we have limited ourselves to a normal, uniform, and triangular distribution. Taking module power as an example, our module is specified as a 270 watt peak module with a 3% positive variance, which can reach 278 watt peak. Now, what type of distribution most accurately describes this variance? The overall production of this module power range in the factory would be recognized as a normal distribution. Here, however, we are describing only the 270 watt peak module. Now, any normal distribution curve can be seen as a collection of small bar graphs, of which our 270 watt peak module is only one such bar graph. So figuratively speaking, the distribution across the 270 to 278 watt peak bin is probably more of a uniform distribution, being a small section of the overall normal distribution. The global horizontal irradiation is a natural phenomenon if ever there was one. So the normal distribution over the year is best described as normal. Ground coverage, module loss due to LID, or light-induced degradation, technical unavailability, and the yearly degradation were categorized by us as a triangular distribution. None of these parameters can be described as a normal distribution, being based upon causation that is not necessarily natural in nature. Ground coverage is based upon how much land we purchase, so it has an upper level based on land price. If land is unlimited and free of charge, we have no distribution. The lower level, unfortunately, is seldom if ever zero. In our context, it is based upon our tolerance for self-shading. Module loss due to light-induced degradation is an interesting case, since we are basing the probability upon our experience and understanding of what the degradation will be. We are quite sure that the light-induced degradation will not be zero the first year. In our experience, this parameter, however, is not published by the module manufacturers and not readily available. We must base our conclusions, therefore, on what is written in the various technical and academic published literature, which usually defines the LID losses today as around 2%. Yet we know many cases of 3, 4, and even 5%. We therefore now run our yield and profit analysis equations 10,000 times, using the parameters we have carefully calculated using the best practices we concluded in our report, Technical Assumptions Used in PV Financial Models. Here we see each of our 12 variables as the output from a Monte Carlo simulation. We no longer have a single value, we have a distribution. We see here quite distinctly the 3 types of statistical distributions we had defined, the uniform, normal, and triangular. The purpose of our exercise is to calculate these values, energy, revenue, and the IRR, or internal rate of return. We now have not a single number, but a value with a probability based upon running all the parameters with their variances. For example, first-year energy production, shown here, uses 8 of our 12 parameters with the variances. Our median is around 280,000 megawatt hours for the first year, with 10% of the values coming in at least with 264,500 megawatt hours. That's more than 6% less than the median value. This then is our so-called P90 value, achieved here running a Monte Carlo simulation on all 8 of the parameters affecting the energy production. Another method for mitigating financial risk is to understand the effect of each parameter on the financial bottom line by using graphical tools to emphasize the interrelation of the various parameters, such as this tornado plot. This type of plot aids decision makers in understanding the relative weight of each parameter and the effect a decision to change a parameter value has on the bottom line. Primarily, it tells us which parameters are most important. It's interesting to note that the turnkey installation cost, foremost on the mind of the financial team, and a point of constant price negotiation attempting to cut costs, has less effect by far than technical unavailability, a direct consequence of too much price cutting during installation. However, in this particular case of the tornado plot, the turnkey installation cost is in fact just statistical noise. This spider plot shows us the effective impact of each parameter. In other words, which parameters are most sensitive to change. It shows us the functional relationship between the parameter and the change from the mean value. In this spider plot, the revenue from energy sales, the slope is an indication of how sensitive the relationship between this value and the change in revenue. This plot can be dangerous, however, because we ourselves choose the boundaries for the maximum and minimum values. The 0 to 100% range in this plot represents a delta that we have decided upon. It's not an objective range. A PV project, then, is a long process encompassing sometimes many years from inception to commissioning and commencement of the O&M stage. As we have seen, the assumed production of the plant is dependent upon the input variables and the initial design quality. These parameters must remain the same from feasibility through design, licensing, financing, and critically at the bidding and building stages. We have to hold true to the original assumptions we made and the level of quality we decided upon during the early feasibility phase, and through the long, dark, empty times awaiting shovel-ready status. If decisions are changed during the financing and bidding stages, then the owner must ensure that the necessary simulations are reworked. Achieving the financial goals of the project depend upon good quality control to ensure continuity. Quality control to ensure continuity is the next message that we want to get across. Quality control is loyal to ensuring that the level of quality designed for will carry through both distinct phases of the project. And while we're talking about quality control, let's have a word about quality itself. An investor with a large risk appetite, opting out of a high-quality project where technical problems are considered unlikely to emerge during the project lifetime, preferring instead a lower quality project where the amount of post-construction troubleshooting, repairing, and replacing may be more substantial, should be made aware of the Andersen Rule of 10, which states that it costs 10 times more to find and repair a defect at every consecutive stage of a project. This table portrays the cost of fixing a fault in each consecutive phase. This is not to say that a project cannot be successful using even substandard equipment or workmanship, as long as the risk of failure and the cost of repairs is accurately translated financially to define the financial cash flow through the 25 years of the project. So an important element of mitigating financial risk is to ensure quality control throughout the project, whatever that level of quality may be. How then do we achieve quality control? We suggest 4 keywords for devising a methodology: strategize, classify, understand, and manage. Strategize. A prerequisite for any successful risk mitigation strategy is to ensure that the overall process is recognized by the top-level decision makers and that this management level takes responsibility for defining an appropriate strategy and assignment of the necessary resources to undertake this process. If the big boss does not actively support quality control, there quite simply will be no quality. The bottom line is to classify risks in terms of occurrence, frequency, and severity in terms of financial impact. This can be accomplished by building a team that includes a wide variety of skills and experiences. A PV plant is a multidisciplinary project requiring a wide variety of expertise. Direct current, alternating current, and medium voltage, even high voltage electrical engineering, mechanical engineering, construction engineering, monitoring expertise, security system, and the list goes on. Upper-level management should then brainstorm with all these professionals to bring out the risks and to discuss cost-effective methods for mitigating them. Then build checklists to make sure all potential risks are identified. Understand by analyzing the root causes of the various risk factors, including possible interrelations between the different factors. Identify the specific most important influencer that may challenge the financial performance of the project. And most important, manage. If the big boss top management is not actively supporting quality control, there will be no quality, and the chances for achieving the business plan will be greatly reduced. The top management must be made to understand the importance of continuity of the design level of a plant and the effect changes will have on the financial plan. So, our conclusions. To conclude, we have analyzed the technical assumptions used in a financial model. We have analyzed the areas of weakness in a PV project, and we have seen some levels of accuracy between the design calculations and the finished project. We have quantified the cost of a technical risk by adapting the failure modes and effect analysis to PV development, and the use of the cost priority number, or CPN, in evaluating the cost of a mitigating action. And we have mitigated the financial risk in the business plan by challenging the operators of the simulation program used for calculating first-year energy generation, calculating the major indices of the business plan using both the parameter and its variance, using graphing tools to visualize the interdependence of these variables, and ensuring that a rigid quality control regimen exists that will enable the design parameters on which the business plan was built to remain intact from feasibility through to the O&M. And with that, I thank you for your patience and turn the presentation back over to Fernando.
Okay, great. Thank you very much.